Welcome to Live Effects. I'm Dave and this is the channel where I do stuff with effects. Last time when we left the island we created these vines. Not bad for a prototype, but there's still a lot of work to do. So let's get to it. At the moment these are just simple lines. They have different angles and a randomized length, but they are perfectly straight. So obviously we need a noise. I will create that noise with a Wrangle node. In one of my earlier videos I explained how I took the typical VOP node and inspected the generated code. With what I learned I could replicate that in the Wrangle node. For details I will add that video in the description. But this is the gist of it. First I set the color to black and then I want to create a red gradient. I can get that gradient by taking the point number and divide it by the amount of points that are there. The result goes into the red channel of color, but since both of these values are integers, I need to cast them into floats. Now I have red lines and black lines, which is not what I wanted. The problem is that these points are not sorted depending on their position on the y-axis, but I can change that with the sort node. And that's more like it. The points with the highest position in y become red, while the points that are closer to the bottom get closer to black. I want to use the amount of red color to control how much noise gets applied. But to create noise in a Wrangle, I need a bunch of values. And it would be practical if I also had UI elements to control them. So let's start with those. These are the same you would find in the VOP node. We have frequency, an offset, an integer for the turbulence, an amplitude, the roughness, and attenuation. Hit accept and generate the new parameters. For starters, let's initialize these values with typical noise values. We can adjust them later. Now that we have these values, we can go back to the editor and start creating the noise vector. An easy to use function for noise is oNoise. The parameters it needs is the position multiplied with the frequency minus the offset, the turbulence, the roughness and the attenuation. Then the noise has to be multiplied with the amplitude. And after that, all you have to do is add the noise on top of the current position. And the function works. We have noise displacement on all of our points. We did not yet use the red color to control it. So let's do that. When we just multiply the noise with the red color channel, the red parts are displaced, while the black ends of the vines are untouched. We need to reverse that. Just use a fit function and all values that previously ranged from 0 to 1 are now ranging from 1 to 0. That's closer to what I want, but this noise is a bit too strong. So first I increase the frequency and then you could try to adjust the roughness. But in this situation, I found the vines look better if I increase the attenuation. This is much better, at least for my taste. And then maybe turn down the turbulence to 3. And last but not least, at the moment, when the color is bright red, there's no noise at all. Maybe we should keep at least a little bit. So instead of remapping it to 1 to 0, maybe try 1 to 0.15. Now we always have a bit of noise, even at the start of the vine. Now that this is done, we don't need the red color anymore. So this point in time is as good as any to create a color ramp to give these vines a typical greenish look. And as you can see, I did not go for the VOP node. I made it a new hobby of mine to find solutions for your typical workflows in a Wrangle. I need to create a color gradient. So I need two colors. I name them C1 and C2. These UI elements allow me to use the standard color picker. To make it easier to see what happens, I choose the color red and blue. Then, when I go back into the editor, I can bring in these two color vectors by using the created parameters. If you want to address a vector, you need to type in CHV. The function I'm going to use is called spline. This function will return an interpolated value along a polyline or a spline curve. The function will need quite a lot of parameters to work properly. And this is what you need. A string array for the type of interpolation, but it has a default value. So basically you don't need to fill that. Then you need the positions on the ramp, and in our case we only have the 2. And then we need an array that holds the different colors that we provide for the color gradient. Of course, we need to fill that array with the colors we created before. When we have all of that prepared, we can then put all of these values into the spline function. We start with the basis array. Then we need to define the position on the ramp. For that we use the attribute curveU. That attribute was part of an earlier video. It holds the value from 0 to 1 depending on the position on the vine. Next, the spline function needs the colors and the ramp positions. The result of this function will deliver a vector. The content of that vector will be a color, somewhere between the ramp positions, taking into account the value of the attribute curveU. The result is a simple gradient that we now can control with the UI element. So let's try to find the colors appropriate for our vines. Maybe a slightly brighter green at the start, and that transitions into a more darker green. Maybe I make the difference a bit more subtle. Yeah, that looks quite alright. Then I want to have a selection of vines on which I attach leaves. So I create a delete node, set it to delete by range, and I'm going to select one of 6. This node will contain the vines without leaves, and when I copy this node and change it to delete none selected, I get the vines for the leaves. The points on the vines represent the positions where I'm going to attach the leaves. But as you can see, at the moment there are quite a few of them. So let's create a resample node to turn that down just a bit. For level of detail I type in 0.15, and for the length I also choose 1.5. Now that we have the points, we still have to create the leaves. Let's go over here and create a new space. This area will hold all of the nodes that are necessary to model them. We start by creating a simple line. The type is NURBS and the direction of the line is 1 in X and 1 in Z. Put the length to 0.6, and if you want to deform it later, increase the point amount to maybe 12. Now I need to be able to address the last point of this line. And here's one simple way to do it. Create an attribute Wrangle. The Wrangle runs over all of the points, and if the current point number is equals the function endpoints, which returns the amount of all points minus 1, then we have the last point of the line. Then type in @group_last equals 1. By doing that, you just created a group with only this point in it. We want to copy something onto that point, and that is a circle. This will be the placeholder for our leaf. Let's adjust the radius so that it gets an oval shape. Then, when we have a shape that could go through as a leaf from a distance, we're going to copy that to the point. And as I said, we only want to copy it on the last point. So in the target points, choose our created group last. I want to connect the leaf circle with its border on that point. So go back to the circle and add the negative radius into the center. Now the point is connected to the outside border, but the angle of the leaf was off right from the start. So let's create a transform node and correct that rotation. That's more like it. Now let's create a merge and combine the circle with the original line. Next, create a mirror node. And now we have 2 leaves. Up to this point we didn't care about the size of these leaves. This would be way too big to copy them onto the vines. So let's create a transform node and decrease the uniform scale. In my case something around 0.13. And finally create a null and call it out small leaves. For the case of our vines, we don't need a reference null since we are in the same subnetwork. But later on we have other cases where we could use small leaves. So let's get back to our vines and the points that are supposed to hold the leaves. As I mentioned on my social media, I did have some problems at this stage. I used polyframe to create normals that worked for one side of the island, but on the other side the attached leaves did a twist. so I held the floating island series on hold until I figured it out. And then Entagma came to the rescue. Recently, the guys from Entagma published a video about parallel transport. It was exactly what I needed. To start that approach, let's update the normals of the vines to point straight up. Just type in @n equals 0, 1, 0. Now I kept the following Wrangle almost identical to their approach, so it makes sense to call this the Entagma parallel transport. If you already saw that one, I go through it in the next 6 minutes. So if you want to skip that, I see you on the other side. For the rest of you, here's how it works. The Wrangle goes over each primitive. As you can see, each vine is its own primitive. I need to get the points of that primitive, so I'm going to create an integer array, use the function primPoints with the current prim number. Then I also need the amount of points in that array. To kick things off, I want to have a vector that is pointing from the first point of each vine to its second point. You do that by creating a normalized vector, where you take the position of the target point, here created with the point function and the second element of the point array, and subtract the origin point from where you want to calculate that vector. Then I need a vector that is pointing straight upwards. And since we just did that for all of our points, we can simply use the normal of the first point. And then it's getting interesting. We're going to use the cross product. To keep it short, if you have two vectors, the cross product of those two vectors is orthogonal to them. We create a first temporary vector with the cross product of the up vector stored in the first normal and the tangent we saved on the first point. Then we update what is saved in first normal with the cross product of the first tangent and the just created temporary cross product. And now the main work starts. To handle the coming information, we need another vector, Entagma called it the bitangent, a float variable, and two vector arrays. Then we're going to loop over almost all of the points of each vine. We use a for loop starting from 0 until that count is not longer less than the point count minus 1. This will leave out the last point on the vine, but we come back to that later. Now we're going to fill the first vector array, called tangents, in the same way we created the initial tangent. We create a normalized vector that is pointing from the current point to the point that follows. This is a very important concept when dealing with vectors. If you want point 1 to have normals pointing towards point 2, you need to take the position of point 2 and subtract the position of point 1. That is the normal that is pointing from point 1 to point 2. But back to our for loop. At this point we can also initialize the normals array. Let's just use the content of first normal. Let's see if we made any errors so far. And of course we did. But it's a minor one. I just forgot one bracket. Now that we have the tangent array prepared, I want to create the same visualizers as Entagma. I want to set the attribute myTangent. I create a for loop that goes over all of my points. Each point gets the value of the related element of the tangents array. Then copy that line and paste it 2 additional times. The second attribute is created by the normals array. The third attribute belongs to that vector bitangent that we did not use yet. Now all of this might sound a bit abstract. And that's why visualizers exist. They help you to debug your project and make it possible to easily check if your coding does what it should. Now this first visualizer is supposed to show you the content of tangent. And it looks like as if the values of tangent are correct. There's a line from each point going into the direction of the second one. Now for the other two, let's just copy this visualizer and create my normal and my bitangent. Now the visualizer for bitangent has nothing to show yet. The visualizer for the normal, the green one, has the same value on each point. The only point left is the last one. This first loop stopped one point before it. And the reason is simple. We can't create a tangent from the last point to the next because there is no next point. But the workaround is also simple. We just copy the values from the point before and write them into the last point. If you look closely, you can see that there are no lines coming from these last points. So let's get back into the editor and add one new value to the tangents array and the normal array. And as I said, that value comes from that array itself by using the index of the element before the last point. To get that, just use the point count -2. Do the same for the normals. And now the lines also appear on the last point. Now we create yet another loop, and this one does the main work of the parallel transport. This time this loop goes over all points. That means we need a bit of extra logic just for the last point, because the first step is to create the bitangent, a normalized vector that holds the cross product of one element in the tangents array and the element that follows it. We already filled the last element of tangents with the value that came before it. The result of a cross product from two vectors that are the same is a 0 vector. The same counts if one of those vectors is already 0. But if the length of bitangent is 0, we reach that point. In that case, we have to fill the normals array for the last element. For every other case, we proceed with the main logic. Make sure bitangent is normalized, and then we create the amount on how far we want to rotate the normals. In this method, we get that amount with the arcos function, which returns the inverse cosine. And we feed that function the dot product of two neighboring elements in the tangents array. Now to do the rotation, we need an identity matrix, sometimes also called unit matrix. And while we are on the subject of matrices, would you guys be interested in some beginner introduction to matrices? I understand that is a topic not easy to grasp if you're not used to them. So let me know in the comments. But now that we have the matrix, the amount, and bitangent functioning as axis, we can create a rotation. That rotation is now saved in the matrix rod. And now I set the normal of the coming element in the normals array to the current normal, but rotated by the matrix. When we now take a closer look at the normals, you can see how they are now pointing away from the tangent. And most interesting, in the slope of the vine curve, it has this nice rotation gradient. But we still can see the axis that was used to create that rotation, the bitangent. That visualizer is still on and set to red. It is not visible because the last vine at some point reached its last point, which resulted in bitangent to contain null. Now when everything is done, bitangent gets set to a normalized vector with the cross product with the current normals element and the current tangents element. And that allows us to see all three axes that create that rotation. So far so good. But how does that help us to place the leaves? At this point I deviate a little bit from Entagma's example. First, instead of using a VOP node, I also create the next step in a Wrangle. The next step is to create the orientation that the leaves will use when I copy them onto the points. Orient is a global attribute. When you fill it, Houdini knows what to do with it. And to do that, we need a matrix 3, which is basically a list of 3 vectors. We set that matrix to our created attributes, my bitangent, my normal, and my tangent. And then we can use that matrix to fill the attribute orient. But orient has a specific format in Houdini. It's a quaternion. With the function quaternion, we can convert our matrix into that. And now we can finally copy our leaves onto those points. Create a copy to point node, connect the leaves and our points with orientation into the second input. And here they are, perfectly rotated along our vine curves. Now that we have the Entagma parallel transport in place, it allows us to easily manipulate the vine rotation. I want the vines to have a slight rotation the longer they get. So let's create a new float amount that has the product of the curve hue attribute, a random value based on the point number, and a fixed value I call degree. Let's set that parameter to 1 just to test the effect. Then we do another rotation. We use the already created matrix, the defined amount, and for the axis we just use the up vector. Now when you take a look at the vines, you notice that with each point it slightly rotates around the y-axis. But in between you see a few points breaking that pattern. That gives it a more organic and natural look. When we increase the degree value, you can see how the final rotation gets bigger and bigger. For my taste, the right value would be something between 0.8 and 1.1. Now I'm quite happy with that result. The only thing left to do is create a merge node to combine the vines without and with leaves. And there you have it. VEX-driven vines displaced by using a VEX Noise, colored by using a VEX spline, and populated with leaves using Entagma's fantastic parallel transport method. Let's render this out and see what we got so far. And here's the rendered version of the island, combined with everything we built until now. This was one long episode and I hope you found something useful. I see you next time.